As you might know, I love using the Arduino Nano or Arduino Pro Mini in projects. Since their heart, the Atmega 3208P microcontroller, offers a lot of useful features while being easily programmable through the Arduino IDE. I even made a few videos about how to use them. That is how much I enjoy working with them. But sometimes, at least for me, you notice its limitations. Maybe the 10-bit resolution of the ADC with voltage steps of around 4.9 mV at 5 volts is not precise enough. Or the maximum 8-bit PWM frequency of 62.6 kHz is not fast enough. Or you need more than 2 external interrupt pins for your project. That is why in this video I will introduce you to this development board, which is also known as the Blue Pill. Its heart is the STM32 F103 C8 T6 32-bit ARM microcontroller, and it can be bought from China for only $2 and best of all can be programmed through the Arduino IDE. So let's not waste any more time and find out what advantages and disadvantages this board offers in comparison to the traditional Arduino Nano / Pro Mini. Let's get started. This video is sponsored by JLC PCB. Upload your Gerber files for review and then order high quality PCBs for ridiculously low prices, currently even with free shipping, and turn your project into real products. To program the microcontroller, we need to firstly connect it through its micro USB port to a power source and grab an USB to Seriell Converter breakout board. After selecting its 3.3 volt mode, since the STM32 operates at 3.3 volts voltage levels, we can connect its ground pin to ground, its TX pin to the A10 pin and its RX pin to the A9 pin. And as soon as the converter is connected to a computer, we can start the Arduino software, add this link to the additional boards manager URLs, and install the STM32 F1XX boards library through the boards manager. As a first example sketch, I created the simplest code I could think of, an LED blink sketch. The only difference in comparison to the traditional Arduino programming so far is the pin name, which are all named according to the silk screen on the development board. And after I connected an LED with resistor between the selected pin and ground, I changed the boot 0 jumper to 1 and selected the here shown settings in the tools options in order to upload the sketch successfully. As you can see, the uploaded code does work without a problem, but what is important to note is that when the microcontroller resets, its program gets erased. Unless of course you change the boot 0 jumper back to a 0 before resetting or repowering the board. For a more demanding test, let's try out the digital read and the serial output function, which pretty much follow the same programming language we are used to. And after uploading the codes and connecting the selected pin to 5 volts or ground, we can see on the serial monitor that everything works fine. But wait a minute, I connected it to 5 volts, even though this is a 3.3 volt system. The reason is that a couple of pins are 5 volt tolerant, while others are not. And by the way, this pinout diagram was a great support when working with the board. But anyway, another awesome feature is that the inputs not only offer integrated pull-up resistors, like the Arduino does, but also integrated pull-down resistors. And with the digital inputs out of the way, let's try something a bit more complicated, like PWM. The difference this time is that we must declare the utilized pin as PWM and use the PWM write function. The analog write function would still work, but it would only offer an 8-bit resolution, like the Arduino, while the PWM write function offers a resolution of 16 bits. That is a difference of 255 steps to 65,535 steps, which can often be quite useful. And if you're wondering where I got all this information from, then look no further than the Leaf Labs documentation. There pretty much every necessary feature and function of the Blue Pill's programming is very comprehensible explained. But getting back to topic, after uploading the codes and connecting the pin to the oscilloscope, we can observe the PWM signal. But sadly, its frequency was only around 549 Hz. The problem is the timer 1, who's responsible for the pin and thus the PWM signal. In order to change its prescaler to 1 and thus speed the PWM signal up a bit, I added lines to the codes according to the Leaf Labs documentation, uploaded it, and realized that this only improved the frequency a bit. The still remaining problem is that the timer register counts up to a value of 65,535, while the clock frequency of 72 MHz would represent 1 second. Thus, by dividing 72 MHz by 65,535, we would get a frequency of 1098 Hz, which is basically what we measured before. So the solution is to simply decrease this 16-bit timer, aka overflow value, to something like an 8-bit value, and adjust the PWM write value accordingly. After uploading, we now got an 8-bit PWM signal just like the Arduino, but with an increased frequency of 281 kHz. And by pushing the timer to the maximum, we could even get a PWM signal with a frequency of 36 MHz. But speaking of timers, how about creating timer interrupts? Well, I have to say, by once again utilizing the Leaf Labs documentation, it was even simpler to implement a precise 1-second compare interrupt than with the traditional Arduino programming. And as you can see, it also works like a charm. You only have to be careful when using the same timer for an interrupt and a PWM signal. That usually does not work out very well. Next, let's add a potentiometer to one of the 10 analog in pins and create a simple sketch that outputs the converted analog value to the serial monitor. Once again, the only difference is the declaration of the pin. The rest is the same as with traditional Arduino programming. And after uploading, we can adjust the potentiometer to output values through the serial monitor between 0 and 4095. This range of values represents a 12-bit resolution, so voltage steps of 0.8 mV, instead of the usual Arduino steps of 3.2 mV due to its 10-bit resolution. Finally, let's set up an external interrupt, which once again, due to the given documentation, was super easy to implement. And if you're wondering why exactly pin PA1, then there's no particular reason for that, since all of the pins feature the external interrupt function, which according to this table should give us a total of 15 external interrupt pins, instead of only 2 of the Arduino. Now of course, the Arduino also offers pin change interrupts on all of their I/O pins, but they are not as fast and easy to use. And after uploading the new code to the STM32, the external interrupt routine seems to also work without a problem. So let's come to a conclusion. The Blue Pill offers more memory, more I/O pins, more PWM pins, more timers, more ADC channels, more external interrupt pins, and a couple more features, while also providing an overall higher resolution and speed. Programming is even simpler than traditional Arduino programming, and you can work with variables with a length of up to 64 bits. The only big disadvantage is that not all Arduino libraries are compatible or ported over yet. But you can always look for advice on the STM32 Arduino forum. So for me, this development board is an awesome Arduino alternative for more demanding projects. I hope you enjoyed watching this video. If so, don't forget to like, share and subscribe. Stay creative, and I will see you next time.